I will be taking you through this demonstration today. Let me just start by sharing my screen. And showing you the magnet interface. The first thing we'll do here today will be to show you how we can import geometries into MagNet, and we'll work from there and to give you an idea of how well this works. So the first thing we'll do is we'll go to our import feature, and we'll import a SAT file. As you can see, we have several different import formats that we can read. These are available to users as an option. Our standard format is SAT, and we'll look at a SAT file now. So I'm going to choose this voice coil, and as you can see, the import brings in the geometry, and we're now ready to apply different changes to the model to make it usable for final modeling. So the first thing we want to do is we want to assign materials. And what I'll do is I'll choose some materials that are generic. We'll make the top plate and the bottom plate here into using cold rolled steel. We'll also assign aluminum to the side brackets. The coil is just part of the top here, so we'll make that out of the copper. So we'll choose copper from the list here. The coil is actually set up in two parts here, so that we have internal faces to assign coil windings to. And the last part for this voice coil motor is to have assigned permanent magnet materials. As you can see, permanent magnet materials are a little bit different because now we have to also assign the magnetization direction. So we'll take it so the magnetization direction is going to be along the y-axis in this case. And for the other side, we'll make it so that it's in the opposite direction, like that. So we now have assigned all the material properties to our model. Let me just show you also that when you import, of course, the names can be quite complex here. As you can see, there's not much differentiation between different parts. So let me just rename these. One of these to let's say the bottom plate here, and of course we can go on and show this for others as well. But before, let me just go to a model where I actually have already done that to the model. So here we have the same model, but now I've renamed things, as you can see. I've also taken the coil parts out and made them separate from the whole voice coil body, and this will help us with doing certain operations. The second step we will be doing for modeling is we need air around the object in order to be able to, because the fields will propagate through the air, and hence we need to also model the that part. So I'm going to use some of these predefined volumes here to be able to do that. So we'll use a cylinder. I'm going to call it an air volume, and we'll assign the material air, make the radius 175 and a length of 100 millimeters. And I won't use the scaling from the tool, from the cylinder generation tool, but I'll do this manually so you get a better idea of how we can actually also move parts around simply by, first thing will be to rotate. We'll rotate about the x-axis, and also we'll move it by shifting the volumes up a little bit or down a little bit and forwards or backwards in space here. So if I look at the voice coil, you can see it's now centered. If we look at it from the top, you can see it's all totally enclosed within the volume. The next step will be to actually create a coil. And to do that is I'll just turn that off here, and we'll just bring up the coil parts here, and we'll select the terminal faces that we want. These are going to be these two terminal faces here, which are the terminal faces. This is equivalent to actually putting a slice into the coil and taking out leads from that coil. So this is the equivalent of doing that, and we'll just make a multi-terminal coil out of that. And as you can see, we now have this coil object that gets created at the bottom. Also have to take that coil object and give it some properties. We can do this from the coil tab here. The first thing we want to do is we want to make this a stranded coil because we want to put in number of turns, and we're going to put in 20 turns. And we're not going to be using any kind of circuit, so we'll use the built-in source that's part of the coil, and we'll put in 1 amp into that coil. So as you can see, we've actually set up for solution quite rapidly here, and we're ready to actually solve. Now we can actually build models differently, not just by import. You can also, using our drawing tools, for example, create a drawing in space and move it around, and also either by making a component by extrusion, either translationally or rotationally, or even by doing a multi-sweep. The multi-sweep is very useful for creating coils, and for that we have the 3D coil creator, which already has some predefined models. So for example, we have a racetrack, preformed, straight rectangular, toroidal, and a lap winding. And these, of course, is just a matter of putting in different parameters here. And we also can create those by defining the path of the center of the cross section as well. So this is a very useful tool. In order also to build volumes, we can also use booleans that are to do such as union, subtract, and intersect rather with it to create volumes of other types as well. Now, one of the things I went rapidly over was actually showing you how you could actually assign materials, and I went to this material page, and to give you an idea, we have many libraries of materials. Most of these are categorized by types of materials. For example, brush materials, commonly used materials, you get some permanent magnet materials, but we also have some manufacturer-specific libraries such as vacuum schmelz and magnet materials and steel materials, as well as magnet quench. And we will be probably adding others as other manufacturers provide us with their data. There are also user material libraries, which are libraries that you create yourself. And then there's the model materials library, which is the library of materials for the current model, and that is actually saved. That library is actually saved with the model itself, so it makes the whole file very compact and easily to share with other users of MagNet. Just to give you an idea how we can actually generate a material, a user material, we can just do this from the new user material pop up here, and you can take copies of the materials in the other libraries. The other libraries here from brush materials on down are read-only, but we can take a copy of that and actually change the material properties that are currently there and add it, create a new material which will be saved in user materials. Some of the properties that we can assign are going to be permeability or BH curves, conductivity or resistivity, permittivity, and there's all the many others as well. Some of them having to do with multiphysics, such as thermal analysis and some fluid analysis as well. This is not for CFD, but rather for specifying the material type in the thermal analysis. We can enter linear materials. For example, let's assume that we're using isotropic real materials, so you can put in a temperature a relative permeability, and if it's a permanent magnet material, and also a coercivity. And you can also do the same thing at several temperatures. It can also be nonlinear, isotropic. So if you go back here, then we just enter the pH, the H versus B data, and this also can be at different temperatures. And of course, we can also do some lost materials and so on. Let me show you an example of a material that has some loss information assigned to it. So we'll go to these ASI materials, which are common. Let's say a M19. So we look at the properties of that. As you can see here, I have brought up the BH curve page and the loss page. And as you can see, the loss data is all entered into this table. And from that table, we actually calculate the coefficients of the Steinmetz equation, which we will then be using for doing core loss calculations during our post-processing. All right, let me now just show you some of the advanced features, some of the other features that we can work with in MagNet. And the first one is going to be that we're going to be able to actually change the mesh assignment in the actual model itself. And the way to do that is to actually select. You can do it in many ways. The most common way is to actually select the object and change the properties of that object. For example, here are the three basic mesh refinement tools. And if you look at different levels, you'll see that these tools appear. And here I have actually changed two of these tools to be able to change the mesh density. And you can also do this at the different levels, as I said, even to the face level. And also, you could actually also do it on the edges as well, and even to points. Another very, very useful feature, which is using of mesh layers. Mesh layers are very useful when you're doing very thin, when the field is going through a very thin layer of a solid piece. And to do that, I can choose the face here. I will bring out the properties, the mesh properties here, and go to the mesh layers. And you can select different mesh layer types. These can be uniform layers, logarithmic, or user-defined layers. For example, if you take uniform layers, then you can also apply to both sides of the face, inside of the component or outside of the component. So you let the system determine what direction to take. And you can change the number of layers and the layer height. Of course, if we were to go to logarithmic, this would change a little bit. Same thing but essentially you can always specify whether it's inside, outside, or both. And of course, this will help you in doing a lot of the skin effect problems, for example. Now, a lot of vendors talk about adaption. Adaption is not really a meshing issue; it's more of a solving issue. So I'll discuss that a little bit later and show you an example of that. Another feature that I want to add to this model is I want to be able to move that coil. So let me just turn some of these items invisible here so that we can see what we're doing. And what I want to do is I want to be able to move the coil, rotate the coil above the magnet. So the first thing I need to do is to define a parameter. And if you look down at the bottom of the list here, I've actually defined a parameter called angle. Currently it's set to 0. And what it will do is it'll look at how I've assigned it. Now, if I assign it to the coil parts, so you can see there's one part of the coil, and you can see that I've set the rotation angle here and given a parameter. And here's our parameter angle here, and it's got a It's essentially dimensionless, so I define it as a degree, and we also define the angle, the axis about which the coil is to be rotated, and you get the same thing for the second part of the coil, as you can see it over here. Let me get back to our parameter here and show you the effect of actually changing that value. Currently, so it's 0. I've defined 0 as being right down the center of the magnet. So let's change it to -20 here, and just apply that, and you can see that the coil is actually rotated to a different position. Of course, we can change that to any position that we want here. Let's choose some point on the other side now, and you can see that it actually has moved the coil in space. There are a lot of parameters that we can assign it to. As you can see, there are all these parameters that are defined for each object, because each of these selections here is a different object. You can choose these different objects and be able to parameterize any of these quantities that appear in these parameter pages. So there are many parameters that you can change, including meshing, for example, as you can see here. So this can all be done through a parameterization tool. So let's have a look at a complete model now, where I've actually assigned the same thing to the model, but now I've made it a little bit more complete by changing the angle parameter here is now got a full set of solutions, or a full set of values. So I can actually, we'll take this out of the way again here. Hold on a second. We'll take the top plate away again, and we'll have a look at what happens here. Well, when we go to the problem tab, these are all the problems that are set up for solution. As you can see, there are 17 problems for solution in different positions. So I can choose, for example, position 9 here, and you can see this is my center position. I can choose whatever, and I will be able to get a solution for all of those in a single run. This is going to be very useful, because when I actually take the results, I can look at global results, which are calculated at the very end of the solution. And here, of course, what would be interesting is to actually look at what the force looks like, or the torque rather, that's applied to that coil. And if we just click on graph selection after, so we're looking at the magnitude of the torque graph selection, and you can now see how the torque varies as a function of this problem ID. So each problem here is a point along that curve. Now, this charting tool is also very useful, because you can extract the data from that. You can also export the data into different files as well for reports and things like that. Other quantities that are of interest, for example, would be flux linkage. If you're looking at calculating inductance, ohmic losses in conducting parts, core losses. In this case, we don't have any materials that have any core loss calculations, so we don't have anything calculated. We can calculate current, and with a couple problems, you can actually get the temperature. Of course, in this case here, the temperature is fixed, so there's not much useful information here. We can view also the results. Since this is a field solution, we can view the results as a field. And we have three different fields that we can view. There's a contour plot, shaded plot, and an arrow plot. The default plot in this case is going to be the shaded plot. So what you're seeing is the flux density in the various parts of the volumes. We can also choose to look maybe at an arrow plot of the current density at the same time. So let's update that, and we'll see the current density through the coil as well as the flux density. And there are other ways to actually take different parts of the model and view different fields. You can view inside, for example, through slices and things like that. One of the most useful tools is actually using animations. And as you can see, it's just by simply clicking on an animate button here, and we'll be able to see. I've actually have an animation loaded here, and we can see how that looks like here. So we'll just start it playing. Let me just slow it down a little bit. And you can see that how the coil field changes as it moves over top of the permanent magnets and so on. So those are all very useful tools. And one of the nice things about the animations, of course, is that we can actually save that animation. If I click on Save here, I can change that as an animation, and you can see I can also export that to an AVI format. So it's just a matter of clicking on Save As, and it will generate an animation. Of course, the AVI can be viewed in on many other computers. Simply, most Windows computers can actually read those without any difficulty. Let's change speed a little bit and change our model here and have a look at another type of actuator. And this is going to be a simple solenoid actuator. Let me just rotate this around here so that we can see a little bit better what's happening inside here. So what we'll do is that basically we'll be putting a DC current into the coil here, and we'll look at what happens when we turn on that current, what will happen to the plunger, which is this part here. In order to do this, we'll be using two different things. The first thing we'll be using will be a circuit. So if I look at here, bring up a circuit window, you can see the circuit editor has been brought up. Now, the coil here is a coil that we've created using the methods that I showed you before, but we've actually placed it in a circuit with a DC current source. As you can see, the waveform is simply constant. We've put in a capacitor in here. Other things that we can add would be voltage sources, resistors, capacitors, switches, some specialized switches as well, such as position control switches for motion analysis, commutators, and so on. Of course, we have a connection tool, so we can just by clicking on the different parts, we can actually connect all the parts together. The second thing we used in here was to actually create a motion component. Now, the motion component actually is the plunger here. As you can see, if I expand that, you can see there's a plunger component, and a motion component has many different properties. They can be current-driven or load-driven or velocity-driven. For this case, we've chosen it to be load-driven. It can be linear or rotary. And so here, again, we're using linear motion, so it's just up and down motion in the Y direction. And for load-driven problems, we have the opportunity to also add external loads, such as, and these can be are cumulative, so I could have a constant load, a time-dependent load, a position-dependent load. It can be position-dependent, but depending on the direction of the motion. For example, if it's position going in the positive direction, then it would be defined in this table, in the negative direction in this table, and then also speed-dependent loads. So you can do certain things such as maybe some speed-dependent damping, but there are other parameters as well that we can use to change the load. One of the also useful features especially for solenoids will be bumpers and stops. Here we've defined some bumpers so that if it hits the bumper, it actually will bounce off of it. So we've positioned the bumper with respect to its reference position, and we could also have added a stop. A stop is different from a bumper in the sense that the solution will stop at that point. Other types of loads that we can put in is actually viscous damping. We can also add springs. So you can see spring constant, spring rest position, and so on. So there's actually a spring associated with this device as well. And once you've solved the problem, you will now be able to view the solution, the various quantities as a function of time. So you can see, you can just by changing this, you can see what the plunger is doing is as a function of time. We can also graph that, so you can see the way that the plunger has moved over time. And of course, we can also generate animations for that as well. So you'll actually see the plunger moving. One of the things that is also differentiates MagNet from many of the other packages out there is our solving capability. First of all, we have 4 different solver types in both 2D and 3D. As you can see here, we have the full list of solvers. We have the static 2D solver, which is for magnetostatic problems where you have either permanent magnets and or currents and coiled DC coils and so on, that kind of thing. We have an AC solver where you have time harmonic, so sinusoidal inputs. We also have a transient solver, which allows you to have basically any kind of waveform that you want. You can define it as sinusoid, or you can define it as totally arbitrary, piecewise linear, and so on. And of course, this transient 2D with motion, which is what we have here. You have the same thing with 3D as well. And the other thing that's important to know here is that our problems are also not just first order, but they can also be as from first to fourth order in 2D and from first to third order in 3D. Now this differentiates us again from our other vendors in the sense that we have multiple orders, and in 3D we have, in 2D we have to, everything has to be the same order, but in 3D you can actually have volumes having different polynomial orders. And in fact, this allows us to do something very very sophisticated when it comes to adaptation. If you remember, I mentioned adaptation before, so let me have a look at what adaptation gives us now. And adaptation can be either H-adaptation, which is where the mesh is refined, where the error, where an error parameter is indicated as being very large. And in 3D, we also have P-adaptation, which is where those elements are actually bumped up in order. And we can also have HP-adaptation, which allows you to combine, start by doing some H-adaptation and finishing off with some P-adaptation. So let me bring up a model that shows that, and we'll quickly show you what the effect of that doing that is like. If we start by viewing the initial 2D mesh here, you can see how it's very coarse. I only have one element across these volumes here. So what I've done here is I'm going to take the adaptation options here. I'm going to click on H-adaptation, and we'll solve this again. And we'll solve it static 2D, and we'll view the solution mesh now. So there's the original mesh, and this is what the solution mesh now looks like. And as you can see, the mesh has been refined, and you can see you've got a lot more elements in the coil here, and you've got a lot more elements in the target here. So this is also a very useful tool for, especially for when you're first working with this product, to understand how to actually where to put elements, for example. So this is a good training tool as well. And as a final aspect of some of the tools that we actually provide with, that you can purchase as options with MagNet, one of those is what we call the system model generator. The system model generator takes a model such as this one here and actually creates a mapping of the response of an actuator, for example, as a function of current and position. And this model is totally independent of the finite element model, and it can be used in system simulators such as Simulink and other system simulators such as maybe Mentor Graphics, System Vision, Sabre, and many others as well. So that's one of the tools that we can provide. We also have the ability to export to using to MPCCI. MPCCI, for those who don't know what that is a method of transferring between different types of physics packages. So, for example, we can generate the forces acting on the different volumes and export that through MPCCI to a mechanical tool to look at mechanical loading. This could be used, for example, for evaluating bending and deformation of the surface, which could lead to acoustic noise. And of course, that information can then also be done in acoustic simulators. So you can actually also determine the noise content of an object doing it that kind of in that example. We also have a tool that's built into MagNet, which is very useful, and that's a scripting tool. The scripting tool allows you to do anything that you want with the interface. You can generate volumes, you can generate pretty well anything that you want. And I'll just give you an example of a script that I've put together very quickly here. And you can see this one here just draws basically 4 lines, and you can see these are the coordinates of the corner points. And I'll just run that now. So I'll just run that script. And as you can see, I've drawn that rectangle just by simply running that script. Of course, this is a very simple script. You can also make it much more complicated, create volumes and so on, create coils, and so on. So that is pretty well what I wanted to show you today. I guess we'll leave it open for questions now. So we'll try to our best to answer your questions.